Section 3.3, Rates of Change and Behavior of Graphs. In this section, you're going to find the average rate of change of a function. You're going to use a graph to determine where a function is increasing, decreasing, or a constant. You're going to use a graph to locate local maxima and local minimum. Use a graph to locate the absolute maximum and the absolute minimum. So here is a few formulas that you need to recall as we work through this section. Remember that the slope is equal to the difference in y over the difference in x, or rise over run, or the formula y2 minus y1 over x2 minus x1. The point slope formula, in order to create a line or create an equation of a line, is equal to y minus y1 equals m times x minus x1, such that m is the slope. And then there is the slope-intercept formula, which is equal to y equals mx plus b, such that m is the slope and b is the y-intercept. Here is a warm-up activity. In your own words, explain what the slope is for a line. So the slope is basically the rise over run. The slope is the rise over run. That is basically what the slope of a line is. Find the equation of a line with a slope 2/3 and a y-intercept of 0, -5. So we identify m is equal to 2 over 3, and we have b is equal to -5. We can use the slope-intercept formula in order to find the equation of the line. So y equals m is 2 over 3x plus b, so plus -5, which can be written as y equals 2/3 x minus 5, and that is the equation of that line. Find the equation of the line that goes through the points 3, 5, and 0, 7. So the first step here is to figure out the slope. The slope is equal to rise over run, so 7 minus 5 over 0 minus 3. Or you could label these x1, y1, x2, y2. So y2 minus y1 over x2 minus x1 is equal to 7 minus 5 is 2, and 0 minus 3 is -3, so it's -2 over 3. That is the slope. And then we can use what we call the point slope formula. So we can say y minus y1 is 5 in this case, equals m, which is -2 over 3. Doesn't matter where you put the negative at, either at the top or at the bottom or in the middle. It doesn't matter, just indicates that the slope is negative, times x minus x1, in this case it's 3. So the point, I use this point, x1 and y1. And now we're just gonna simplify the function. So the first step is to distribute the -2 over 3 inside of the parentheses. So we will get y minus 5 equals -2 over 3x minus -2 over 3 times 3. These three cancel together, and we have y minus 5 equals -2 over 3x. Negative times negative is positive, so plus 2. And the final thing is to add 5 to both sides of the equation. So the final answer is going to be y equals -2 over 3x plus 7. 2 plus 5 is 7, and that is the equation of that line that passes through those 2 points. What is the relationship among graphs of lines with the equation y equals mx plus 2, where m is any real number? These lines, they have the same y-intercept, which means they're going to pass through the same point on the y-axis, which is equal to 0 and 2. So that is the relationship among all graphs of lines that have that equation. And because the slope changes, that means these lines are going to be at different slopes. Here is a little illustration of what I'm trying to say. So that is basically the y-intercept, which is 0 and 2. And you could have any graphs passing through this point regardless of their slope. As you can see, all of these lines share the same thing, which is passing through the same y-intercept. What is the relationship among graphs of lines with the graph y equals 2x plus b, where b is any real number. So notice how these graphs have the same slope, but they have a different y-intercept, which means they are going to be going at the same slope. However, the y-intercept is going to be different. So they're going to be parallel to one another. They're going to be parallel to one another such that they have the same exact slope. Okay. For example, here is a graph. A line that has a slope of, let's say, 2, which basically means rise is 1 and run is 2. So let's say it's one of them is going to go through this line right here. And then another one is going to be parallel to that. Another one is going to be parallel to that, and etc. So they have the same slope, however, the y-intercept is going to be different from one another. So they're going to be parallel. Finding the average rate of change. A rate of change describes how an output quantity changes relative to the change in the input quantity. The units on a rate of change are output units per input units, like distance over time, which is the speed basically. That is the average rate of change in distance over time. The average rate of change between two input values is the total change of the function values, the output values, divided by the change in the input values. If the relationship between x and y is not linear, then the ratio is called the average rate of change of y with respect to x. So in a linear relationship, we call that the slope. In a nonlinear relationship, we call that an average rate of change of y with respect to x. So here is the formula. The average rate of change is the change in output divided by the change in input, or delta y over delta x. In other words, it's f of x2 minus f of x1 divided by x2 minus x1. Let's look at an example here. Find the average rate of change for the given function or graphs. So we would like to find the average rate of change of the function f of x equals 2x squared minus 9 for the first interval, let's say. So I'm going to call this x1. I'm going to call that x2. So I will need to find f of x2, which is basically replacing each x with 5. So 5 squared minus 9, which will give me 2 times 25 minus 9. That is 50 minus 9, which is 41. And now I'm going to find f of x1, which is basically replacing x with the 2. So 2 times 2 squared minus 9, which is equal to 2 times 4 minus 9. That is 8 minus 9, which is negative 1. So now that I found f of x2 and f of x1, I can apply the formula. I'm going to say the average rate of change equals f of x2 minus f of x1 divided by x2 minus x1. Notice how we have to align these. So you can't say f of x1 minus f of x2 over x2 minus x1. They have to align. The indices have to align. So this is equal to 41 minus negative 1 over 5 minus 2, which will be 41 plus 1 over 3. That is 42 over 3. Which is equal to 14. We don't have units here, so we're going to keep it like that. So that is basically the first part. I'm going to try to minimize this and move it to the side. So that is basically the first one. Similarly, you can find the average rate of change for the interval 4 and b. So in this case, f of x2 is equal to, this is x1, this is x2. It's equal to 2b squared minus 9. And then f of x1 is equal to 2 times 4 squared minus 9, which will be 2 times 16 minus 9. That is equal to 32 minus 9, which is equal to 23. So now we can apply the average rate of change. I'm going to be lazy here. I'm going to say average rate of change. That is not an actual abbreviation that you'll see anywhere. I'm just using that just for short, which is going to be F2, f of x2, that is 2b squared minus 9, minus f of x1, which is 23, over x2, which is b, minus x1, which is 4. So now we're going to simplify the numerator. It's going to be 2b squared minus 32 over b minus 4. Now, if I pull 2 out as a common factor from the numerator, I will get b squared minus 16 over b minus 4. And now, if I would like to factor the numerator, I will get b minus 4 times b plus 4 over b minus 4. So these will cancel together, and I will have at the end the average rate of change is going to be, I'm just going to write it here, it's equal to 2 times b plus 4, or 2b plus 8. And again, we don't have units here, so we're going to keep it like that. I'm going to actually erase all of this work to do the last one. Hopefully you're taking notes. Pause the video, and you can basically pause and or go at a lower speed if I am going too fast. So this is x2, this is x1, and this is x2. I'm going to find f of x2, which will be equal to 2 times 3 plus h all squared minus 9. If I want to simplify this, first I need to expand 3 plus h all squared, which will be equal to 2 times 3 times 3 is 9, 3 times h times 2 is 6h, plus h times h is h squared, minus 9. And then I'm going to distribute the 2 inside. So I'll distribute the 2 inside. You will have 18 plus 12h plus h, 2h squared, minus 9. And now all we need to do is to combine 18 and 9, 18 and negative 9. So we will have 18 minus 9 is 9, plus 12h plus 2h squared. I'm going to leave it like that. And then f of x1, I'm going to do it here, is equal to 2 times 3 squared minus 9, which will be 2 times 9 minus 9. That is equal to 9, which is 18 minus 9. And now the average rate of change, again, I'm going to be lazy, is equal to f of x2, which is, I'm going to rewrite the expression so the highest power is first, 2h squared plus 12h plus 9, and then minus 9 minus f of x1, all divided by 3 minus, 3 plus h minus 3. So the 3 is going to cancel with 3, and then I will have average rate of change equals, these will cancel. I'm going to pull 2h out as a common factor, and let me actually minimize this so I can work. So I will have 2h, and then what's remaining is going to be h plus 6, all divided by h. The h is going to cancel with h, and then we're going to end up with 2 times h plus 6. And that is the average rate of change for the last part. Sometimes you don't have the formula for the function like it was given in the first question. Sometimes you will be given a graph instead of a formula, and you'll be asked to find the average rate of change. So how do we find that? Notice how x1 is equal to 1 and x2 is equal to 5. So I'm going to determine these on the number line here. So that is x1, and here is x2. In order to find f of x1, I'm going to draw a vertical line. And then when it intersects with the graph, I'm going to graph a horizontal line to determine f of x1. So f of x1, which is 1 in this case, is equal to 5. Similarly, I will graph a vertical line from x2 until it intersects with the graph of the function, and then from there I will draw a horizontal line to figure out f of x2. So f of x2 is equal to 7. And now I'm ready to apply the formula average rate of change, being lazy again. F of x2 is 7 minus f of x1 is 5 over x2 is 5 minus x1 is 1. So that will be equal to 2 over 4, which is equal to 1/2. And again, this is unitless because I don't have units here. Increasing, decreasing, and constant functions. This leads me to the topic of increasing and decreasing and constant functions. So, if the average rate of change is positive, which means if you scan your graph and the graph tends to be growing or going upwards, so imagine that you are standing here and you're climbing, so you're going upwards. This is what we call an average rate of change that is positive. Then the graph is increasing over the interval that is given. Then the graph is increasing from left to right. So in this case specifically, I will be able to say that the graph is increasing over the interval AB, and the interval has to be open in this case. So the interval AB, because the behavior at a specific point is not known. Similar here, I'm going to say, let's say you're starting from the left again. So you're standing here. So we always stand from the left. Notice how the trend is going downwards. So in this case, you will say that if the average rate of change is negative, the graph is decreasing from left to right. So I will be able to say that the graph is decreasing over the interval AB, again, open interval, because we don't know that the behavior of the graph at a certain point, okay? And then if you are, let's say the third time you're standing here at the left, and then you're not going up, you're not going down, you're going in a constant manner. So you're going this way, you're going constant. So if the average rate of change is 0, which means there is no change, then the graph is constant. So I can say basically the function here, or the graph of a function, is constant over the interval AB, basically. We always study increasing and increasing of a graph over a certain interval. As part of exploring how functions change, we can identify intervals over which the function is changing in specific ways. We say that a function is increasing on an interval if the function values increase as the input values increase within that interval. Similarly, a function is decreasing on an interval if the function values decrease as the input values increase over that interval. The average rate of change of an increasing function is positive. The average rate of change of a decreasing function is negative. And the figure below shows examples of increasing and decreasing intervals on a function. So if we're studying the behavior of a specific graph, we're going to divide that graph into specific intervals such that we identify where the behavior of the function changes. So as I start here from the left, notice that I will start increasing first. So I will increase, so the function is increasing on this interval specifically, but the behavior changes at this point right here. So I'm going to stop right here at this point, and I'm going to say the function is increasing over the interval from negative infinity, because it doesn't have a start, all the way to x equals -2. We always study the behavior horizontally. We never study it vertically. So some of you will make the mistake of saying, oh, the function is increasing from negative infinity to 16. But that is not how it works. We study the behavior over the x-axis, not over the y-axis. And then notice the change here in the behavior where the graph decreases from this point right here all the way to this point. So we can say here the graph is decreasing over the interval from -2 all the way to +2, -2 to +2. So that is where the graph is decreasing. And then notice another behavior change, which is the graph is increasing one more time over the interval from 2 all the way to +infinity. So we're going to say increasing from 2 to +infinity. So basically, we can combine these two together. We can combine the increasing intervals together, and we can say that the graph of this function is increasing over the interval from negative infinity to negative 2, union from 2 to positive infinity. And then it is decreasing over the interval negative 2 to positive 2. These increasing and decreasing behaviors creates what we call the maximum and minimum, which are basically called local maximum and local minimum. A value of the input where a function changes from increasing to decreasing as we go from left to right, that is, as the input variable increases, is called a local maximum. So if the behavior changes from increasing to decreasing, we create what we call a local maximum. And here is an example of a local maximum. If a function has more than one, we say it has a local maxima, because maxima is basically the plural of maximum. Similarly, a value of the input where a function changes from decreasing to increasing as the input variable increases is called a local minimum. And here is an example of a local minimum, where the behavior changes from decreasing to increasing. The plural of minimum is local minima. Together, local maxima and minima are called local extrema. So if we're talking about local maxima and local minima, we can just say local extrema or local extreme values of the function. Often, the term local is replaced by the term relative. So you can hear also people say relative maximum and relative minimum, meaning the same thing, which is a local maximum or a local minimum. In this text, we will use the term local. Note that a maximum or a maxima happens when the graph changes from increasing to decreasing, and a minima happens when the graph changes from decreasing to increasing. So here is another illustration, as you can see here. So when we talk about the maximum and minimum, the local maximum and minimum, we name the maximum and then the location of the maximum. For example, our first example of maximum was this point right here. So we say we have a local maximum of 16. So the highest point the graph reaches is 16. Where is that going to happen? It happens where x is equal to negative 2. So that is the position of the maximum. So that is how we identify the maximum and minimum. Similarly here, you're going to say we have a local minimum, which is this point right here, local minimum of negative 16, which is the lowest point the graph reaches, basically. And it occurs when x is equal to positive 2. So it happens here, which is where x is equal to positive 2. Okay. Again, a local maximum and local minimum happens where the behavior changes. So you're not going to tell me that this point is a minimum and that point is a maximum, because the graph just continues going and it doesn't change behavior. So it has to change behavior to identify that local maximum or local minimum. Are the maximum minima values included in the intervals of increasing and decreasing? The answer is no. And the reason why is because the behavior at that point is not known. I don't know if you're standing here, if you're going to go down or up. So it is not included. The behavior is basically there, is stable. We don't have an increase or decrease in the behavior. And that's why the point of the maxima and minima is not going to be included in the intervals if they are increasing or decreasing. If you look at the toolkit functions and analyze if the function is increasing or decreasing, basically you can take that as an exercise and you can basically answer these questions. So if I look at the identity function, which is function f of x equals to x, notice how the graph is increasing over all of the real numbers. It is not increasing. It's not decreasing. So I'm going to say increasing over negative infinity to positive infinity. It's not decreasing. If you look at the graph of the absolute value function, it is decreasing here. So I'm going to say it is decreasing from negative infinity to 0. And it is increasing on that part. So I'm going to say it is increasing from 0 to positive infinity. The graph of the square root function, notice how the graph just increases from the 0 to positive infinity, and it's not decreasing. So it is increasing from 0 to positive infinity. Notice how I'm not including the endpoints in these behaviors, because the behavior at a certain point is unknown. If I look at the quadratic function, you'll notice that the behavior here is decreasing. So I'm going to say it is decreasing from negative infinity to 0, and it is increasing on that interval, which is going to be increasing from 0 to positive infinity. The cubic function is increasing from negative infinity to 0, and it is increasing here as well. So it is increasing from negative infinity to positive infinity. So the behavior is always increasing in this case. It doesn't have a decreasing behavior. Notice how the reciprocal function is very unique. So if you scan it from left to right, this part is actually decreasing. And then the behavior stops when x is equal to 0, and then it is decreasing on the other part of the domain. So it is decreasing. It's not increasing at all. It's decreasing, and it's decreasing from negative infinity to 0, union from 0 to positive infinity, which is basically the entire domain of the reciprocal function. So it is not increasing, it's just decreasing on the entire domain. Here is the last piece of section 3.3, which is basically an application. At the start of a trip, the odometer on a car reads 20,736 miles. At the end of the trip, 11.5 hours later, the odometer reads 21,372 miles. What is the average speed the car traveled? So we're going to calculate the average speed, which is the average rate of change. Which is basically the total distance traveled, or the change in distance, over the change in time, or the total time. So the change in distance over the change in time. We were given the change in time immediately, so we can basically say 21,372 miles minus 20,736 miles over 11.5, which is the change in time. And the answer is going to be 636 divided by 11.5, which is equal to 55.30. And the units are miles per hour. So the units are miles per hour. And that concludes section 3.3. I hope everything was clear, and if you do have any questions, let me know.